All right. Hi everyone. In today's video, it's going to be slight deviation from what we have been doing so far. We are going to discuss one code forces question. And before you kind of log off or what is this about, why is this deviation? I really want to touch upon where this question is going to be used in real code basis, right? Where does this knowledge come into place? And that's why I'm not on lead code, I'm on code forces. Just with the experience that, okay, these questions, and I've of course like selectively chosen the question. We are going to cover the solution in this video, but wait for the next video where we will talk about the application of the solution over here. And we'll also try to cover the real code base, some real example, and also explain it to you then how you can use whatever solution you have seen in this video in your software engineering practice, experience, and all of that. Okay. So let's go to this question for starters. So there's a girl, I guess, has a bracket sequence this. So basically, like they're bracket sequences of something of that sort, and they have queries. Okay, so what they want is from 2 to 3, they want to know, okay, how many pairs of brackets you can form, right? So as simple as that, like if I say 1 to 12, so the starting index is 1, the ending index is 12, and I believe that's inclusive. If not, we'll check it out, but it does sound like it's inclusive so far. Yeah, should be. Right. So what they want is they want to know, okay, how many pairs can be formed. As an example, like if you'll see for the third query, required sequence will be this, right, which has one pair. So that's what it does. For the fourth query, required sequence will be this. And then you kind of like figure out, okay, how many pairs can be found. So if you just focus on this, for example, like there's one, and then there is one, and then there is outside brackets, then there is one, and then there is one outside brackets. Okay, so always like focus on this as well. So similar to this, I think what we want is just to count number of brackets that can be formed. Okay, so that's the goal of this video, to understand how we can solve this. Now before we go forward with this, we'll be going through the brute force problem, I mean brute force solution, and we'll also be touching upon the optimized solution. And I really want to talk about like what's the impact of going from brute force to optimized solution. In very important terms, right? We all understand the time complexity, but we don't really understand the time taken as well and the scale of the problem. Over here, they have put some constraints that, okay, the length of the string can go up to 10 power 6, and the characters, sorry, the query can be between, I think, 1 to 10 power 5. So that can be the number of queries you have. So over here, they have 7 queries. They can have up to 10 power 5 queries, and with a string of length 10 power 6, up to 10 power 6, right? So overall, the scale is huge. Okay, so this problem is not going to be easy when you try to take it up to to go to that route where you go with brute force. Can we cover that level of scale? We'll try to understand. Okay, so let's go ahead and solve the problem. All right, so in order to solve the problem, it's very like, I think what we'll probably do is understand this particular thing. Okay, so what we're doing is, like, even when you look at this particular string with your naked eyes, what you're going to see is that you kind of track the number of open brackets so far, and you try to close them as you move, right? So if you look at this, like what you will do is, okay, there's a closed bracket, but there's an open bracket, right? So that means, okay, this is done. So now you don't look back at this particular bracket and then you move forward, right? So similarly, like as an example, when you see this, you know that this is already occupied. So you know that, okay, this is just going to stand around and do nothing. There's no match for this. Similarly, when you go ahead, you look at this, there's an open bracket again. So you don't let go of these two things, right? You know that, okay, these are going to be used at some point of time. Then you look at this bracket, you know that, okay, there was an immediate bracket that was available. You take that, then you see that, okay, there was this one. This was already occupied. So you skip that and you skip and you use this one. So there's a match between these two, right? Similarly, for these two, you know that this is available. Similarly, for this two, and there you go. This is going to just stand around, okay? Now, over here, it's kind of very clear what we're trying to do. We are going to, I mean, we are going through the string one by one, and we are trying to figure out whether for a closed bracket, is there an open bracket available, right? So how will that sound like, okay? Like how are you going to resolve that particular thing? It's very simple. So let's try to, I already have written the code, by the way. So I don't want to spend time writing the code again, but you know what, like let's kind of think about how to further resolve this in a way which kind of gives us an optimized solution. And why is it very slow, right? And the reason it's slow is for every query, what you're doing is you're going through the whole string one by one, right? I mean, that means that you have O of n time complexity for each query, and there are q queries, so it's going to be O of n into q. Okay. And the reason this is very bad in a way is because let's imagine that you have 10 power 6 as the length of the string, which already we saw on the Codeforces link. And then you have 10 power 5 queries. Okay. So this means that we're going to have 10 power 11 number of operations, right? In terms of O of n into q. It's not directly related to number of operations. It can be more than that, but that's going to be like in our calculation, that's going to be number of operations we are doing. And these operations are essentially like we can call it comparisons as well, right? And let's say your CPU suppose 10 power 9 ops per second, and given the process load and everything, it can be lesser as well, or it can be better. But even if that's there, it's going to cost you minimum 100 seconds to solve this problem, right? Which is really bad, right? Like, I mean, if you see, like, our expectation is that it should possibly take even less than that. I don't want to call out that, okay, how much should it take, but this is really bad. Okay, like this is like almost 2 minutes for solving this problem. For the computations that we have right now, 10 power 9 ops per second, it sounds bad. Okay, how do we resolve that? And one thing that you should focus on is not just about the time taken, it's about the repetitive operations we are doing for each query. When you have already gone through the string, right, you should not really be going through the string again, right? Even if it's a substring, doesn't matter, but you're going through the string again and again, right? So that's not a good approach. And wherever you see that you're doing a repetitive operation, right, you should not do that. Okay, so let's now talk about a problem, I mean, the way we can solve it. Okay, and I do want to touch upon, I'm not sure if all of you are aware of segment tree, but we will be showing you an image quickly. Just give me 1 second. So we're going to possibly like show you one image of a segment tree, right? So let's go to segment tree. Yeah. Okay. All right. So segment trees are essentially like wherever there's a query, right? Wherever there's a query and there's a range. So these are very helpful. And the reason these are helpful is because you don't have to go through the whole tree uh, and compute or compare those operations, because each one of them will have a static value at the time of building, right? So what happens is, when you build the tree, you compute all the operations and everything that's needed, which is great, and that's what you should do, right? Whenever you're going through the string, you should try to pre-compute whatever that could be useful, assuming that's not very expensive and you have a trade-off there, right? Once you do that, next time when you come up with a query that, hey, I want 3 to 5, this one already has an answer. Okay, so you don't have to recompute anything. You already know what's the answer for this 3 to 5. So if the starting to end was 3 comma 5, you will already have the answer, right? So that's what a segment tree is about. I don't want to talk about what's the segment tree in this video. I don't want to touch upon quickly on how to solve this. Okay, so the way we are going to cover this is that at the time of building, we are going to have for each node, right? So let's do that. So for each node, what we are going to do is we are going to have three states. Okay, one is matched. The second is like, okay, how many open, unmatched open brackets, and then you're going to have unmatched close brackets. Okay, so you're going to keep for each node, you're going to keep this status. These are the values. Okay, so that means, as an example, let's say that a node has this. Okay, ignore the square brackets. I think it's better if I kind of don't put it here. So let's say that this is what you have. In this case, you're going to have matched s2. You're going to have closed and open as 0, because there's like nothing left. These are like unmatched zeros, right? But similarly, let's say you had this and you had this. Okay, I think this is better, right? So in this case, your matched are 1 because you have, let's try to focus on here. You already have matched as 1. Now there are two unmatched brackets and both are unmatched open, right? There's no closed bracket here. So in this case, here you have unmatched open as 2 and then unmatched close as 0. Now, the reason like I'm kind of showing this through is that just for you to understand what this like state means per node, but very important for you to know that we are going to split this across, right? So over here, what we're going to do is, as I've shown in the image, you're going to reach to the leaf node, And within these two nodes, for example, here 3 comma 4, you're going to merge them into 3 comma 4 again. So 3 individually, 4 individually has a value, right, which is very fixed. If a bracket is open, there is like 0 matched, 1 open, 1 unmatched open, sorry, and 0 unmatched close. Similarly, for a closed bracket, you have 0 matched, 0 unmatched open, and 1 unmatched close, right? So for these values, these are very static. You just need to know whether it's an open bracket or a closed bracket. After that, the merging operation is very interesting. And how do you really merge? Okay, so let's talk about that, because for all of these operations, I mean the segment tree, the merging is very important, right? So how do you really merge, right? So the way you should be thinking about this is, see, let's say that you had this and this. Okay, so the left node was an open bracket, okay, and the right node was closed bracket. So in this case, matched equal to 0, uh, and over here, unmatched open is 1, unmatched close is 0, right? So, and similarly for this one, what do you have? Do you have 0 and 0 and 1, because this unmatched close? So the order is matched, unmatched open, unmatched closed. I'm going to call it Q close. Okay, so that is obvious. Now when you merge this into one, right? Now you see that, okay, it's already matched, and the reason this is going to be in the matched state, uh, to us it's very clear, it's matched now. That you expect the output to be something like this now when you merge these two nodes. But mathematically, the way it's going to work is that you have whatever, like, matched total, let's call it this. So matched left plus matched right. Okay, so I can hopefully call it LMR, right? So let's say that, okay, left one had 5 matches, right one had 6 matches. You combine them, of course they're going to be 11 matches, right? We don't have any query about that. I hope so. Now the reason I have, so far, so it's going to be 0 plus 0 here. Now what about unmatched L, right? It's going to be very simple. You should think about whatever the unmatched L, like over here, how many open brackets were there? Over there, how many closed brackets were there? You figure out the min of them. And the reason I say this is, imagine that you have 3 open brackets here, right? And 2 closed brackets here. Now, can someone tell me how many matches you can get from here? Of course, you can only get 2. And the competition was very simple, that you calculate the min of L comma R, which is like, okay, how many open are in left, how many closed are in R, right? So that's what you do. So this is going to be a constant for us, okay? This is going to be very important. And what this means is, out of the available ones, we have found these many matches that can be formed if we club them together. So that means the new open L is going to be open L plus open R minus this constant, right? And I'm going to call it open new for the new node, okay? Similarly, for closed new equal to close L plus closed R minus const. And the reason, I hope is clear. You found 5 matches out of these open L plus open R, right? When you combine both of them, you were able to form these many brackets that are matches, and that's how you're going to do. So match new is also going to be ML plus MR, right? So this is the formula for merging, okay? And that's what we're going to use. And if you see, this is O of 1. And the reason this is O of 1 is this, because this is a fixed computation we are doing. It doesn't really depend on anything that is related to number of characters you have in the string. It doesn't really depend on number of nodes in the tree. It doesn't depend on the number of queries you have. It's going to be constant time at the build of a tree. Okay, that's what we're going to do. And once we are done, we are going to get number of brackets available for each node. Okay, so I don't want to spend further time. I think it's time to dig into the code. I am going to open the code for you so that we can see through it. Okay. So I am going to open the code. All right. Now over here, let's go through the brute force approach first. What we are doing is, we get the substring. Now the query format is left comma right and the given string, right? So we are going to take the substring, and given that left is inclusive, that's what we're going to do. So imagine that, okay, it starts from, let's say, 1 comma 3. You're going to say, of course, 0 comma 3, because that's how you want, because these are 0 indexed. But that's okay. Number of match equals 0, pending opens equal to 0. What you do is, for each string, you figure out the substring first. This is not typically O of 1, by the way. Like it depends, but should be a view operator if in NumPy array. I'm not sure about lists in Python, I'll have to check. But for ch in substring, you are going to check if it's an open bracket. You do pending opens equal to plus equal to 1. That means you keep a record of how many open brackets we have so far that are available. If the bracket is closed, in that case, what you do is there any open bracket? I'll grab it and I'll call pending match plus equal to 1, and I'll reduce that by minus equal to 1. That's it. This is a brute force approach. It's slow O of n, and I'll tell you why. O of n into q, sorry. If you have q queries, so O of n into q in our case, okay? And let's go down and let's talk about the segment tree, okay? So let's look at how do we really build it, right? And this is very important. We'll come to this probably in a new video. I don't want to cover too much into detail of this segment tree, but you're given a string, you create a segment tree out of it, and whenever there's a query, you just call it, okay? That's all you need to do. In this case, what we are doing is we are initializing all the nodes with zeros over here. If you remember, I told you that each node has a state: matched, unmatched, open, unmatched, close. So these are the three states each node has. And we are creating 4 into n nodes, okay? Now, for those people who are aware of binary trees, the way this indexing works, because for us, it's kind of easier to imagine, okay, that this is a tree. But how do you really store it in memory? Is it in an array form, right? Of course, like it's in a contiguous memory in this case or not? That's a question, right? Now, the thing is, if the node is nth index, the left children is going to be 2 into n, and the right index is going to be 2 into n plus 1. And the importance that you get from fixing this index is because now accessing the children of a particular node is now O of 1 because you know the computation. Okay, so that's something very helpful in general. That's what we are doing over here. We are creating a tree. We are initializing it in array form. Okay, as you can see, it's a list. It's nothing else, right? I hope it's clear. Now you just build it over here. What we are going to do is we are going to build a tree. If the leaf exists, that means if left equal to right, that means we are at the leaf point. We have a logic that says, okay, what should be the value of that particular index? We will come to this make leaf one. It's very important to cover the base case. That's essentially the base case. There you go. Right? As I already talked about it, M unmatched open, unmatched close. If the bracket is opening, it's only a single unmatched open. We're going to call it 1, 0, 0. Otherwise, this is going to look like this. It's kind of very obvious. I'm not going to cover this much in detail. But after this, what you do is, already I told you what we do. From here, we figure out what is the index going to be 0, 2 and 3, 5, 0, 1, 2. If you understand what we are doing is we're trying to figure out the mid index and then cover this into two children. That's what we are doing here. We figure out, okay, build for the left children, build for the right node, and go ahead and do that. And once that is done, please merge these two nodes into one. Now, this merge logic is very interesting. I think this one I've already covered: 2 into n plus 1, 2 into v, 2 into n over here, right? The merge logic we already covered. It's the min of open left, close right. You figure out total matched is this. By the way, this 0, 1, 2, don't get confused. 0 was number of, like, the 0 was m, 1 was unmatched open, 2 was unmatched close. Okay, so that's what you do. That's how you merge, right? Once that is done, you just figure out that, okay, this is the tree value, and done. Okay, at the query time, I will possibly let you all figure it out. It's very simple. You have to realize that, okay, which left or right node traversal should I do? Where should I call? And which part is it I'm looking forward for? And then I have to merge. Merge is over fun, don't forget. Okay. What I really want to cover over here is query. I'm again letting you all go through it yourself, figure out what's the best way, what does it really mean. Because, as an example, if you had maybe this is the best place. No, okay, yeah. If you had a range of 1 comma 5 as a query, which is start comma end, right? In this case, how do you really merge? Which one is the left children that you're looking forward for? Maybe there's a left children already that exists that covers 0 comma 4, and then there is 4 comma 5. Then you just need to merge both of them, right? So just go through that. Maybe we can take a screenshot of this code and go through it. But the very important thing I'm doing over here is I've created one input.txt file using Claude. I asked it to create one for me. And now I'm recording the difference between brute force result and the segment tree result. Okay, so let's do that. Let me quickly go to input.txt and kind of show it to you before you all are lost in this bracket one. This is what it is, and then you have so many queries. You have 10,000 queries, and the scale of this is we have 10 power 5 as the length of the string and 10 power 4 is the number of queries. So I've reduced it a bit for me to not waste a lot of time in computing this. So let's run the script and see how much time does it really take for brute force versus segment tree. That's very important. Let's see. Yeah, there you go. Right. So segment tree took 0.09 seconds. Brute force took approximately 7 seconds. So this was 0.1, this was 7. So you can see the speed up was 70 times. Okay. Now this is amazing, right? I think this kind of shows you that why it's very important to kind of understand that what algorithm we use. A lot of times when you are like solving a problem, these kind of matching pairs and segment tree approaches will come a lot, and in these cases, you have to figure out and understand what's the importance when you go to the scale, right? Like, how does it really matter, right? So, I do have a code that kind of generates, maybe I can do this. I can default this to, let's say, 10 power 2 and 10 power 1, right? So what this will do is it will generate another input.txt for me. And if I run this now, you're going to see there's not much difference, right? So when your scale is less, right, when you only have these many things, it possibly makes sense for you to avoid creating or building a segment tree, which in fact over here it took more time than brute force, right? And the reason was very simple. Uh, in these cases, you are spending time in building the tree as well. Over here, brute force, you're just doing a for loop, and at times I'm not sure if for loops are expanded in Python, but in C++ for when you convert that into assembly, you can expand a for loop as well given the optimization plan, right? As long as the size is considerable, right? So each instruction, instead of jump operations, you have direct assembly instructions, which is better for the machine. Okay, so in these cases, sometimes it can be slower than what you would have imagined, and sometimes you can see that okay, 70 times speed up. It's a good learning for all of us to understand when to call a particular um, solution, when to use it. In the next video, I'm really going to dive deeper into a code base and show it to you how it works, and wait for it, and like until that, maybe spend more time thinking about all of this, understanding this in detail. I'm not going to cover too much in detail. This is not a teaching lesson, but it's more of an exploratory session for you all, that okay, what is possible and why is it important for you to cover these important data structures in computer science, and also understand the use cases. All right, thank you everyone. Bye bye.